All right, here's Weld Quality Module 6, Session 1. Okay, when you guys finish this module, you should be able to identify and describe the various code organizations that apply to welding and their basic elements. Identify the various welding code organizations and their sponsoring organizations. Identify and describe the basic provisions of welding codes. Identify and describe weld continuities and their causes, including porosity, inclusion, cracking, joint penetration, fusion, and undercutting, and unacceptable weld profiles. Okay, perform a visual inspection on a fillet and or groove weld and complete an inspection report. Okay, welding codes and standards. Welding codes and standards are issued by the following organizations: the American Society of Mechanical Engineers, American Welding Society, the American Petroleum Institute, the American National Standards Institute. Codes, standards, and specifications must be rigorously followed. Okay, here's a WPS, or Welding Procedure Specification. Again, this is like the roadmap for your welds. We've got, let's see, 6 or 7 different procedures at West Hills College that all follow this basic format shown here. And these procedures, basically what they do is they give you the information needed to complete the weld. A couple things to remember is if this procedure is not followed, then the weld doesn't meet specifications. So what's on here is what has to be followed. Okay, here's some important things that you guys need to learn. The essential variables. Before we get to that, the purpose of a weld procedure specification is to define and document in detail the variables related to project-specific welds. So the essential variables. So what these are is these 7 items here cannot be changed. So what that means is if you're performing a weld, if any of these do not match the procedure, then that weld will not meet the specifications outlined in the procedure. And those include filler metal classification, material thickness, joint design, type of base metal, welding process, current type, pre and post heat treatment. Right, then we have non-essential variables. Okay, so non-essential variables are items in the WPS that may change within a range identified by the code, but that do not affect the qualification status. And these are amperage, travel speed, shielding gas flow if applicable, electrode and filler wire size, and rod travel angle. Okay, so these can change or vary within a range based on the procedure without a disqualification of the procedure. I'm not sure why this is here. So what we're showing here is a fillet weld gauge measuring a concave fillet weld. Common weld discontinuities. Porosity. Porosity is just basically foreign material in the weld. Inclusions, or porosity, I mean, is holes in the weld, sorry. Inclusions are foreign material in the weld. Cracks, incomplete joint penetration. This can be caused by improper machine setup or improper joint setup. Incomplete fusion. This is improper machine setup, improper work and travel angles can cause this. Undercuts. What happens here is when you're welding and your material's really hot, and you may have your work or travel angle off slightly, it'll create a kind of like cuts at the toe of the weld. Arc strikes. So it's really important that as you guys practice your arc welding, that you get very good at starting starting where you want to start. And because if you have a strike across the top of a plate when we're doing a certification test, it'll actually disqualify the test, so you'll fail. Spatter, 7018 causes a little bit of light splatter when you're welding. What we're looking for is real heavy splatter, which is indicative of having an arc length that's too long or some setup issues and unacceptable weld profiles. Okay, so porosity. So we're going to go over these three pictures here. So we have linear porosity, and basically that's just porosity that's kind of concentrated about a kind of a certain area of the weld. So if you can see in picture A there, they're kind of all lined up right down the center. So linear porosity may be aligned along a weld interface, the root of a weld, or a boundary between weld beads. Uniformly scattered porosity may be located throughout single pass welds or through several passes in a multiple pass weld. And as you can see, it's kind of scattered. There's really no uniformity to it. One thing you want to be careful of, if you end up with porosity on a multi-pass weld, as you weld over that, a lot of times the small amounts of air that can be trapped in there actually start to come to the surface, and the porosity kind of keeps following you up through the weld if you don't close those off in some way. If you're doing a test that allows a grinder, you'd want to grind down to remove that porosity. If they do not allow a grinder, then you kind of have to use the pointed side of a chipping hammer and kind of peen those closed. Peening is not allowed, though, on your final passes, so you've got to take care of it early when you catch it. Piping porosity. So this, it normally extends from the root of the weld towards the face. These elongated gas pores are also called wormholes. They do not often extend to the surface, and the porosity cannot be visually detected. If you guys make it to the point that you're welding with NR232, this is a common problem with 232 when you're first learning how to run it and trying to get the heat correct for it. It will make a beautiful weld that looks great, and then upon cross-cutting or bending, huge amounts of worming or piping porosity. Okay, inclusions. Slag inclusions are real common, guys. When we start doing groove plates, if you've got the machine set up right and you're performing the weld correctly, realistically, you can pass it with a chipping hammer and a hand brush. A power brush is not necessary. If you're needing a power brush, chances are that you've got some other issues going on in your welds. And a lot of times you end up trapping slag in areas that you actually can't even get it out. As we go through more inspections and stuff, at times I've had welds where we bend them and can drop a little piece of slag out after we do the side bends. So you guys will get to see this as we go along throughout the class. Okay, preventing inclusions. Position the work to maintain slag control. Change the electrode to improve control of molten slag. Thoroughly remove slag between passes. Grind or sand the weld surface if it is rough and likely to entrap slag. Remove heavy mill scale or rust on weld preparations, and avoid the use of electrodes with damaged coverings. Okay, this picture here shows different types of cracks. You guys can review this in the book, or if you'd like, open up the PowerPoint and check this out. Kind of make sure you know what these different cracks are, and understand some of their causes. Sometimes it's actually caused by improper base metal and filler metal selection. Okay, preventing weld metal cracks. Improve the contour or composition of the weld deposit by changing the electrode manipulation or electrical conditions. Increase the thickness of the deposit and provide more weld metal to resist stress by decreasing the travel speed. Reduce thermal stress by preheating. Use low hydrogen electrodes. Balance shrink stress by sequencing welds. And avoid rapid cooling conditions. So that's one thing. When we're practicing, the quench tanks are extremely useful to keep the parts at a temperature that's easier to handle. But when we're doing cert plates, those aren't going to go in the quench tank ever. We're going to let those heat and then just cool off naturally. Okay, preventing base metal cracks. Controlling the cooling rate by preheating. Controlling heat input using the correct electrode. Controlling welding materials, properly matching the filler metal to the base metal. Okay, other discontinuities, incomplete joint fusion. okay, or joint penetration. So we can see it there in the top drawing. The one down below, this looks like it may have been some type of open root. And actually, from the looks of that, that picture, it looks as though it's possibly poor setup. One thing, the welding is kind of the fun part, getting to put things together, laying the beads down. But your prep is almost more important than what you do with the electrode once you're ready to weld. If you mess up your prep while you're setting up a test or setting up a weld, it really doesn't matter how good you can weld. It's awful hard to overcome poor setup. Okay, incomplete joint penetration is an excessively thick root face or insufficient root gap are joint design problems that may cause incomplete penetration, like I said earlier. Okay, incomplete fusion, insufficient heat can cause this. Wrong size or type of electrode, failure to remove oxides or slag, improper joint design, inadequate gas shielding, improper electrode angle, and arc flow can all cause this. In my experience in our shop, one of the things that tends to cause this the most has to do with electrode angles. You really, as we start kind of doing these first welds here, and we do our bead pads, the surfacing welds, really being able to visualize what that weld puddle's doing behind you as you're moving along, and being able to manipulate the electrodes so that the bead's being placed where you want it is extremely important. Because if you have that angle off on that electrode, you're not burning into the plate that you want to fuse together. So it's real important. You guys will begin to develop those skills as we go along. All right, overlap and undercut. Okay, overlap is just basically where the weld is too big and it's kind of rolled over the edge of the joint. You want to be really careful about doing this also while you're doing your groove plate, because it can cause a slag trap. Okay, causes of undercut: using a current adjustment that is too high, having an arc gap that is too long, failing to fill the crater completely with weld metal, improper electrode angle or manipulation, incorrect rod travel speed. So the electrode angle is very important when you're doing fillet welds. It'll really cause that. When we do our groove plates, also the heat of the plate has some effect on it. I kind of tease my students that are smokers that when you get ready to put your cap passes on a test plate, that's the time you go out and have a cigarette. Just let the plate cool down a little bit so that it's not extremely hot from being freshly welded. Then go back in and run your cover passes, and you greatly reduce your chances of undercut. If you're not a smoker, don't worry. Please don't start just for welding class. Okay, arc strikes. Arc strikes cause hardness zones in the base metal and can become the starting point of a crack. Arc strikes can cause a weld to be rejected. So as you guys start practicing, this is where it's really important to be able to strike in a certain area, be able to start your weld efficiently without having to mess around with it forever. Okay, acceptable and unacceptable weld profiles. You guys can look at this a little more closely, but basically the dashed blue lines in there kind of show the profile that you're looking for. And we've got ideal and acceptable there, and then we've got multiple unacceptables. So, and as we start doing fillet welds, I'll show you guys how to use the fillet weld gauges to also view this with a tool instead of just kind of visually guessing at it. Okay, elements of a fillet weld. The weld face is the exposed surface of the weld. The leg is the distance from the root of the joint to the toe of the fillet weld. The weld toe is the junction between the face of the weld and the base metal. The weld root, the point shown in the cross section at which the weld metal intersects with the base metal and extends farthest into the weld joint. Size, the leg lengths of the largest right triangle that can be drawn within the cross section of the fillet weld. Okay, so if we look down below, again, that dashed line that makes a triangle within the weld is the fillet weld size. So convex fillet weld actually is a slightly smaller looking fillet weld, but it'll have the same effective size of a concave fillet weld. and they're measured using different parts of the same tool. We will go over that. I'll show you guys in class. The actual throat, it's the shortest distance from the root to the weld face. That's also why a slightly larger looking concave fillet weld is only measured as the same size as a smaller concave weld, because the actual throat is basically the same. Okay, the effective throat is the minimum distance minus the convexity from the root to the weld face. So this only happens on a convex fillet weld, not on a concave. Theoretical throat, the distance from the beginning of the joint root with a zero opening to its perpendicular, that is perpendicular to the hypotenuse of the largest right triangle that can be inscribed within the cross section of the weld. Okay, equal legs and unequal legs. So welding codes require that fillet welds have a uniform concave or convex face, although a slightly non-uniform face is acceptable. Okay, so when we look at leg lengths, when you size a fillet weld, it'll be given as the size of a leg, as shown kind of on the top. Well, actually on both drawings it shows the legs. So fillet welds will be spec'd out as 1/4 inch, 5/16, 3/8, 1/2 inch. Just kind of depends on what the project is and what the weld engineers come up with. And they can be unequal legs as shown down below. Causes for rejection: insufficient throat, so the weld's too small. Excessive convexity, excessive undercut, overlapping, insufficient leg, or incomplete fusion. All right, we're going to just kind of sail through these trade terms. You guys will have these to review as well as a quiz online. You guys can also review these in the PowerPoint. All right, I'll be right back with session 2 PowerPoint.